In the last class, we were looking at the radial part of the Schrodinger equation for the hydrogen atom, and we were searching for solutions for the radial part of the wave function in terms of a series expansion of this form, and we found that unless the series stops after beyond a certain value n, the resultant wave function is going to diverge, it will blow up. So we find that the wave function has to stop, the series expansion has to terminate at a certain value of m, and the coefficients of the expansion have to disappear for all larger values of n. So if we want C n minus 1, all the coefficients up to n minus 1 to be non-zero, and the nth coefficient and the higher coefficients to disappear, then the condition, this particular condition over here, has to be satisfied, where W was the energy in some units and K was the coefficient that appeared in the Coulomb potential. So this condition had to be satisfied, which gave us this relation which finally, written in terms of the energy, gave us this condition over here. So the energy levels of the hydrogen atom, we found, could be expressed in terms of one integer n, and the energy levels were proportional to 1 by n squared. This was the first feature which we found yesterday in the last class. This small n over here was related to the L, the angular momentum eigenvalue, and the number n over here. This capital N tells us that all the coefficients in the expansion beyond this value disappear, and the small n was the sum of this L, the angular momentum quantum number, and the capital N, these two numbers. So coming back to the energy levels, there should be a minus sign here. So the energy levels depend on only one quantum number, this n over here. So if we fix the value of n, for example, if n is equal to 1, then the fact that this small n is equal to L plus capital N, and obviously the 0th coefficient cannot disappear, otherwise the whole polynomial, the whole wave function disappears. The smallest coefficient that can disappear is the first one. So capital N can take values 1, 2, 3, etc. So this tells us that for a fixed value of n, small n, if n for example is equal to 1, capital N has to be at least 1. So for n equal to 1, small n equal to 1, the only possibility is that L is equal to 0, the total angular momentum is 0, and capital N is equal to 1. For n equal to 2, we saw that there were two possibilities. The total angular momentum could be 0, in which case the radial part of the wave function would be a quadratic polynomial, or we could have the possibility that the total angular momentum is 1, in which case, no, it could be a linear polynomial, and here it would be a constant. Similarly, for n equal to 3, we could have three possible cases. But remember that the total energy depends only on this quantum number. So there are three quantum numbers which decide the state of the hydrogen atom. You have to specify this small n, you have to also specify L, and you have to specify m. All three of these together will determine the full wave function. For example, if you fix n equal to 2, which is the second excited state of the hydrogen atom, this is the first excited state of the hydrogen atom, n equal to 1 is the ground state, n equal to 2 is the first excited state of the hydrogen atom. for this case, the angular momentum L can be either 0 or it could be 1. When L is 0, m has to be 0. When L is 1, m could be minus 1, 0 or plus 1. Similarly, if n is equal to 3, let me just enumerate a few of them to make things clear. If n is equal to 3, what are the possibilities? L has to be less than this n over here. So, L could be equal to 2. This has m minus 2, minus 1, 0, 1, 2, and then you could have L equal to 1, which has minus 1, 0, 1, and you could have L equal to 0, which has only 0. So, you can easily find out that for a given energy level n, how many degenerate states there are. All of these are different wave functions, so they are different eigen states, they are different states, they are different quantum states, but all of them correspond to the same value of the energy. They may have different total angular momentum, but they all correspond to the same energy. These are called the degenerate states corresponding to this value of energy. And for n equal to 3, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So, you can work out a general expression for the number of degenerate states for a given energy level. Now, what is the level of degeneracy that you expect for the hydrogen atom problem? Let us just try to see this. So, let us just go back to the Hamiltonian for the hydrogen atom problem. The Hamiltonian for a hydrogen atom problem can be written in this form. It is 1 by 2m, and then we have the radial momentum squared, which is just some derivative in r in the operator, if you write the operator, and then we have L squared by r squared, and then we have Vr. For any spherically symmetric potential, this is the Hamiltonian. Now, you see the Hamiltonian depends on the angular momentum. So, but it does not depend explicitly on the z component of the angular momentum. It is spherically symmetric. So, it makes no reference to does not make any reference to any particular direction. It is because it is spherically symmetric. So, it does not depend explicitly on any individual component of the angular momentum. It depends on the square of the angular momentum. So, based on the symmetries, you would expect it to not depend on m, which is the eigenvalue of the z component, because the z component of the angular momentum does not appear anywhere in this. So, from the symmetry of the problem explicitly, from the symmetry of the problem, you would expect it to depend on L and on some other quantum number which will tell you the radial part. So, from the symmetry, we would expect it to depend. This is from symmetry, we expect this dependence. So, we expect the energy should depend on these two quantum numbers, one which will tell you what kind of a radial wave function, which particular radial wave function it is, and one which will tell you the angular momentum, because the Hamiltonian or the energy depends explicitly on the angular momentum squared. So, you would expect it to depend on this, but it turns out that for the Coulomb potential, that is 1 by r, it does not depend on L. So, although the Hamiltonian depends on the operator L squared, for this particular potential, the Coulomb potential, the energy E does not depend on the angular momentum state. For any other, this is something which is accidental. It is only particular to the Coulomb potential, and you cannot say that you expect this by looking at the Hamiltonian or looking at the symmetries. It is not obvious. So it is a feature only particular to the Coulomb potential. For any other potential, any other spherically symmetric potential, you will find that the energy levels depend on this some principal quantum number n, which will tell you what kind of the radial wave function. In addition, it will also depend on L. So, but it will not depend on m. For a spherically symmetric wave function, in general, it will not depend on m. If you have a potential which is not spherically symmetric, which has got some preferred direction, then the energy levels will depend on m as well, because there is a preferred direction. So it will depend on this all three quantum numbers. But in general, for a spherically symmetric potential, it will depend on 2. For the Coulomb potential, we find this accidental degeneracy that it depends only on one of the quantum numbers. It does not depend on the angular momentum state. So this is an unique feature of the Coulomb potential. Now, let us work out the wave function, some of the wave functions for the hydrogen atom. So we have seen that the wave function has got 3 parts to it. Let me write down the wave function again, and then we have to put together all the bits and pieces that we have worked out. So the wave function psi will be a function of 3 quantum numbers now, n, l, m, and it is a function of r, theta, phi. And we have seen that this can be written in terms of 3 or 4 different parts. So the first part, which is very simple to write down, is ylm. So the first part is the angular part, which is y l m theta phi, and we have studied this part in some detail, and given L and M we can write down what this function is going to be. So this is the first part. The second part is there is a 1 by r, because we had defined G as some f by r, so there is a 1 by r over here. And then there was exponential e to the power minus square root of w into r. We had defined u as some e to the power minus square root of wr, and that function u turned out to be r to the power of l plus 1 into that polynomial, which was a function of r. So there was a polynomial. So let us put some symbol for the polynomial. So let us put some symbol. So let us say it is capital P of this kind, capital P, which is a function of r, and this the order of the polynomial depended on the difference of L and N on capital N. So capital N was defined to be N minus L. So this is a function of both, or you may say it is a function of N minus L. So we have to now work out this W also depends on the number N, because it is the energy. W is proportional to the energy, and the energy is different for different quantum number N. So we have to work out 2 things. We have to first work out this W, and then we have to work out this polynomial for different cases. So let me first work out what is the W. So W n is equal to, so let me show you the definition of W. W was equal to minus 2me by h cross squared. So let me put that here. It is minus 2m by h cross square into En, and En, if you remember, is, so let me retain these terms here, and Em was minus E square by 4 pi epsilon naught into 2 A naught by n squared, where A naught was the Bohr radius. So this was the energy of the nth level. And what does this give us? Let us put it all together now. So let us also use the definition of this. So we have 2m E square by h cross square 4 pi epsilon. Now let us look at the definition of the Bohr radius. Sorry, there should not be a minus sign here. So the Bohr radius is 4 pi epsilon naught h cross square by m E squared. Yeah, so we can see here 4 pi epsilon naught h cross square m E squared. The two will cancel out, top and bottom. So this is equal to 1 by A naught square into n squared. This is Wn, and the square root of Wn is equal to 1 by A naught n, which is what we would expect, because A naught is of the order of, is something of the order of length. It's a length scale, and here also r is a length scale. So we get exponential. This exponential over here is now e to the power minus square root of Wr, Wnr. This is equal to e to the power minus r by n into A naught. So the length scale for this exponential is n into A naught. So for the nth excited state, the length scale gets larger and larger. The exponential falls off slower and slower. The exponential falls off fastest for the ground state. So this, we have worked out what this part is. Now let us look at this polynomial. So to look at the polynomial, let us first look at the recursion relation which is involved. So the recursion relation is this. So we want to now find out the relation between some arbitrary c and the c which appears before that, in a situation where Cn goes to 0. So let us do it. So we are given n, the total quantum number, the principal quantum number, and L, the total angular momentum quantum number. So we know this implies that n is equal to, this tells us that Cn is equal to 0 and all the higher coefficients are equal to 0. Now let us find out what is the relation between some arbitrary Cm and Cm minus 1. So let us use the expression which we just obtained for the square root of W. So we have in the numerator 2 by A naught n into L plus m minus k. Now let us see what is k. So k is equal to 2m e square by h cross square 4 pi epsilon naught. Now this is equal to 2 times, so let us see if we can write this in terms of w or in terms of the bore radius. So just we have m e square by h cross square 4 pi epsilon naught and the bore radius is m e square 4 pi epsilon naught h cross square. So this thing over here is equal to 2 by a naught squared, right. See, this is equal to 4 pi epsilon naught square h cross square by m e square is a naught, and here we have m e square by 4 pi epsilon naught h cross square, which is a naught square, and the factor of 2 remains on top. So k is 2 by a naught squared. So we have to use this here. So we have minus only a naught, right? So 2 by a naught. This divided by, here we have L plus m plus 1 and we have L plus m minus L into L plus 1. Now this can again, the denominator can be simplified slightly. So if you look at the denominator, let me just expand the denominator. So the denominator, there is one term over here which is L into L plus 1, which will cancel out with this L into L plus 1 here. So I will not bother to write that term. Let me just write that term also. So this will become L into L plus 1, L into L plus 1 plus m into L plus 1 plus m square m into m plus L into m. So first I take the L multiplied by L plus 1, I take the m multiplied by m plus 1, the m remains, so I take m and multiply it here, L and multiply it here, which gives me these 4 terms, and I have minus L into L plus 1, so this cancels out with this, and what I have left is over here. So what we get is Cm by Cm minus 1 is equal to, so I can take this whole thing outside, so I have 2 by a naught outside, and then in the numerator I have L plus m by n minus 1. There is a 1 by n here, so L plus m by n minus 1, and in the denominator I have m into L plus 1 plus m square plus Lm. I can take the m common, so I have m into L plus 1 plus L, which is 2L, this L and this L combined to give me 2L plus m plus 1. So I have 2L plus m plus 1. So this is the recursion relation for a fixed value of n and L. So with these two inputs, let us now go ahead and start our calculation. We shall only calculate a few of the eigenfunctions. So let us first calculate the ground state, which is very simple to calculate. So let us first calculate the ground state, which is psi 0, 0, that is the only possible ground state. So, psi 0, 0, 0 as a function of r theta phi. I will not determine the normalization coefficient, I will just leave that for you to determine. We know what y, the spherical harmonic with L equal to 0 and m equal to 0 is. It is nothing but a constant, right? Y 0, 0 is a constant, it does not depend on theta and phi, so we need not bother about this. Sorry, n cannot be 0, what are we doing? It is 1, 0, 0, right? So this is what we have to calculate, because if for n equal to 0 it blows up, it is meaningless. So we are calculating the ground state, which is 1, 0, 0. So here we have r to the power of L is 0, r to the power of 1. We have r to the power of 1 here also. So these two cancel out. What we have here is e to the power minus e to the power minus r by a naught, because W1 is just 1 by a naught. So the exponential gives us e to the power minus r by a naught. The polynomial is a polynomial of order 1. No, it's n is equal to 1, capital N is equal to 1 in this case. N is equal to n minus L, which is equal to 1 in this case, which tells us that this implies that C1 is equal to 0. So the only non-zero coefficient in that series expansion, only non-zero term is C0, some constant. So the wave function has been determined. So we now find that y psi 1, 0, 0 r theta phi is some arbitrary coefficient which I am not writing down, we can easily find out what it is, into e to the power minus r by a naught. So this is the ground state of the hydrogen atom. Quite simple. It is nothing but an exponential function which we can plot over here. So it has the value 1 at r equal to 0, and then it falls off exponentially, never going to 0. It just dies away exponentially. And the length scale for this exponential decay is a naught, the Bohr radius. So this is the ground state wave function. There is a coefficient of normalization which you can easily determine. Now let us look at the first excited state. So the first excited state is n equal to 2. For n equal to 2, there are a few possibilities. So the first possibility is L equal to 0. So if L is equal to 0, there is only one value of m, which is m equal to 0. So let us work out this. Psi 2, 0, 0 r theta phi is equal to so again let us put back our original expression. Yes, here. So L is equal to 0. If L is equal to 0, so we are considering the case, let us keep it here. We are considering a case where n is 2, L is 0, m is 0. So again we have y 0, 0, which is just a constant. So I shall not bother with this. It is again spherically symmetric, doesn't depend on theta and phi. L is equal to 0. So this is r to the power of 1, which cancels out with the r to the power of 1 over here. The exponential is now e to the power minus r by 2a naught. So that is the first difference. So we have exponential minus r by 2a naught. So if this function, if the ground state looks like this, then the exponential decay will be much slower for the first excited state, because the length scale on which it falls off is larger. This is the first thing. Let us also calculate this p, the polynomial. So now n is equal to 2 minus 0, so it is equal to 2, which implies that C2 is equal to 0. Let us work out how much is C1. So C1 by C0 is equal to, let us work this out. So here we know the relation between C1 and C0. So this we can just put in the values of L, m is equal to 1. M is 1, L equal to 0. So let us put in the values. Or this we can, okay, so we can put in the values. This we can also write as 2 by n a naught. In the numerator we will have L plus m minus n, and here we will have m 2L plus m plus 1. So in this case n is equal to 2, so this 2 cancels out. We have 1 by a naught. Let me put in the values now. So we have 1 by a naught. In the numerator we have 0 plus 0 minus 2, and in the denominator we have no, there is something wrong. Oh yeah, m is equal to 1. This is not the m which is appearing here. That is what is creating the confusion. So let us put some other symbol for this too. Okay, it doesn't matter. So m is 1. We are finding out the first coefficient, 1. And here we have 1 into 0 plus 1 plus 1. So this gives us minus 2. So this is equal to 1 by a naught. And we have 2L, so this is 0. M is equal to 1 and L, 1 is over here. So we have 1 minus 1 in the numerator, which is minus 1 by 2. So it is minus 1 by 2 a naught. So C1 is equal to C naught into minus 1 by 2 a naught. So now we can write down the polynomial. The polynomial, we can take the coefficient C naught outside, which will be some normalization coefficient, which we will fix later. And here we have 1 minus r by 2 a naught. So this is the form of the one of the wave functions corresponding to the first excited state, which is psi 2 0 0, and we can just plot roughly what it looks like. So this is psi 1 0 0, psi 2 0 0 will have one zero crossing at when r is equal to 2 a naught, and it will fall off slower. So it will look something like this. It will have a zero crossing and then fall off exponentially. This will fall off exponentially like this. This will fall off exponentially slower. The overall normalization has to be worked out. You should not believe these figures. This is just a kind of schematic diagram. Let us also work out the other possibilities for the first excited state. The other possibility is n equal to 2 we can have L equal to 1. M can now take 3 possible values, m equal to -1, m equal to 0, m equal to 1. So we shall not bother about this, let us just keep it as an index. So psi 2, 1, 0 r theta phi, this is equal to so let us now put in the forms here. So now we are dealing with the case when n is equal to 2, L is equal to 1, and m can have all these values. The value of m doesn't matter as far as this is concerned, so we can just leave it here. So we have an overall function which we shall not determine. We have already worked out these functions, so we know what this function is. So I can put m here. And we have explicitly worked out all 3 of these spherical harmonics in an earlier class. y10 turned out to be cos theta, y11 and -1 turned out to be sin theta into e to the power I phi e to the power minus I phi. We have already worked this out. So this is some function of theta and phi. So these wave functions are no longer spherically symmetric, they have some theta phi dependence, and these are dipoles. So the L equal to 1 states are dipoles. Now let us work out the r dependence. L is equal to 1, so here we have r to the power of 2. Here we have r in the denominator, so one r will cancel out and we are left with r, and we have e to the power minus r by 2a0. Let us work out the polynomial. So the polynomial, now what is the value of n? N is equal to 2 minus 1, so it is equal to 1, which implies that C1 is equal to 0. So the only non-zero term is C0. So only non-zero term is C0. So it is now some coefficient over here which we shall not bother to write down because there is an overall normalization coefficient. So this is the other wave function corresponding to the second excited state. There are 3 such different wave functions, all of them which have the same radial dependence, only 3 different functions for the theta and phi part, and there is one function which we have just determined for the, so yeah, here. So the state n equal to 2 has got 4 different wave functions which we have worked out. One of them has no theta phi dependence, it has got only a radial dependence. The theta phi dependence is a constant, which is y2, 0, 0. This is one of the first excited state wave functions. There are 3 more first excited state wave functions corresponding to different values of m. This has got 0 total angular momentum. This has got total angular momentum 1. Similarly, one could work out the higher and higher wave functions, and the radial part of these wave functions can be expressed in terms of Laguerre polynomials. I shall not go into the details of this anymore. This is given in any textbook, so one can just look up the detail, which you get by just summing up certain number of these terms in the polynomial, and they turn out to be Laguerre polynomials. Let me just tell you a qualitative feature of the energy spectrum. What does the energy spectrum look like? And then we shall stop today's class. So what does the energy spectrum look like? N equal to 1. This is the ground state, and the energy E1 is minus 13.6 electron volts. So this is the energy of the hydrogen atom in the lowest level, the ground state. So if this is E1 and let us say this is 0, the energy level 0, then this difference from 0 to here is 13.6 electron volts. So when an electron goes and combines with the hydrogen atom, goes to the ground state, then it loses 13.6 electron volts. A free electron has 0 energy. Suppose you have a free electron and free proton, the total energy is 0. When the whole thing combines to form a ground state hydrogen atom, 13.6 eV of energy is released. Now there are intermediate energy levels, so let us also draw that. The level spacing is proportional to 1 by n squared. So the difference from 0, minus 1 by n squared, so E is n is proportional to minus 1 by n squared. So the larger the value of n, the smaller is the value of energy. Also the spacing keeps on getting smaller and smaller as you go to larger and larger n. So the energy levels look something like this. The energy spacings are large to start with, and then they get smaller and smaller and smaller. As you approach this, the energy levels are going to be very, very close together. They're going to be very, very close together. Beyond 0, you have a different sort of energy spectrum. These correspond to the positive values of energy when the electron and proton are free. The total energy is more than 0. Here the energy levels are continuous. For negative energy, the energy levels are discrete. Once the energy crosses 0, where there are free particles, the energy levels are continuous. You have a continuum spectrum. So here the energy levels approach each other very close, get closer and closer, and finally you have a continuous range of spectrum above 0. So there are various transitions there are various radiation is emitted whenever there are transitions between these levels, and there are different names for these different lines. There are Lyman alpha, Lyman beta, then there are Paschen, Balmer, etc. I shall not go into the details of that. The higher energy levels, some of the lower energy levels, the excited states, are observed on Earth. So here you can do experiments where you can excite the hydrogen atom to its first excited state, second excited state, third excited state. But as you go to the higher excited states, the size of the hydrogen atom gets bigger and bigger. And for very large values of n, the size of the hydrogen atom is of the order of n into a naught, is what we saw, right? Something like this. This is the size. So as you go to higher and higher energy levels, the size of the hydrogen atom gets larger and larger. Now the hydrogen atoms, if you have on Earth, they will have some density. Now if the size of the atom gets comparable to the volume available for each atom, then obviously there are going to be collisions which will just not allow those things to be there. But in outer space, it has been observed where the densities are much lower, very high Rydberg levels, very high values of n have been observed indirectly, because you find radiation. So the radiation which will be emitted when, say, the hydrogen atom makes a transition from n equal to 100 to n equal to 99. This will be the energy released here will be very small. So it may appear somewhere in the radio or something like that. The energy released in these parts will appear in the optical or ultraviolet, where the energy released is because the energy released is much larger. Here the energy differences are very small, and the radiation may occur in the radio waves. So there are radio observations which seem to indicate that hydrogen atom in very excited states does exist in outer space, in the interstellar medium. Such hydrogen atoms have not been observed on Earth. Okay. So I shall stop the discussion of the hydrogen atom here. In the next class we shall move on to something altogether new and different.